Okay, today we are going to introduce, or I'm going to introduce to you the concept of the derivative of a function. And just for purposes of discussion, we'll call that function f. So the best way to understand this is with a graph. And we're going to use the notion of average rate of change. If you'll recall, we talked about that. The average rate of change from a point X to another point. And I think when I discussed average rate of change, I used the labels X1 and X2, but you can also think of it as some variable X and then a distance. Actually, we'll just take X to be fixed, but the distance from X to the next point is what's going to vary, and that is X plus H. So here's X, and then you add to that H, and it brings you over here to X plus H, okay? And you can kind of see this is where this is going. We're interested in the slope of the line between the 2 points that lie on the curve. And let me just draw this line straight, or at least try to. Okay, so the slope of that line is the difference quotient that we've talked about in the past. And if we plug X into our function f, the output is going to be f of X. And if we plug in X plus H, this height will be f of X plus H. So the slope is the difference quotient. We take the difference between the y values divided by the difference between the x values. Okay, and this gives us the difference quotient. So we are interested in this difference quotient as h gets smaller and smaller and smaller. In other words, this point is going to be, as h gets smaller, we're moving this direction, right? So h is getting smaller, so this distance is getting smaller, so it's getting closer and closer to your starting value of x. And let me just draw the progression there. Okay, so we have, and as I get even closer, these lines are called secant lines. And the slope of a particular line is the average rate of change. But as you let this h get smaller and smaller, you're getting closer and closer to this point here, and your line is getting closer and closer to what we call the tangent line. And the slope of that tangent line is the derivative at the point x. Okay, the slope of this red line here is the derivative of f at x. So x is just one particular point. Obviously, if I had put x in a different spot, maybe over here, I would have a different tangent line. A tangent line touches the curve at the point, but does not cross the curve. So that's important to note about tangent lines. And they represent the slope, which is the derivative, represents the instantaneous change. So all of these lines are calculating average rate of change over an interval from x to x plus h. But this particular line, so the derivative is defined to be the limit as h approaches 0 of your difference quotient. That is the definition of your derivative, and that just simply represents the slope of the tangent line at that point. Okay. So basically you're taking the change of the function on average and you're over an interval and you're collapsing that interval down to such a small length that you're actually at a point, and that gives you your tangent line. This is the instantaneous rate of change. Instantaneous means at a single point, at an instant. Often this horizontal axis is the time, you know, in the real world, it's often representing time. Okay, any questions so far? The best thing is to look at some examples to kind of get a feel for how this works. So this is the theory. Now I'm going to move to some examples. I want to find the tangent line for f of x equals x squared at the point when x equals 1. Okay. So the first step, since we're looking for the tangent line, we want to find the slope of the tangent line. That's our first step. Okay, find the slope of the tangent line of f of x equals x squared at x equal 1. This is the derivative, and the notation for the derivative is f prime of x. And remember, by definition, it's the limit as h approaches 0 of our difference quotient, f of x plus h minus f of x divided by h. So I need to calculate this difference quotient for our function. And that would be the limit as h approaches 0. Now, what does it mean to evaluate f at x plus h? Well, you just take your x plus h and replace x with that x plus h right here. So this piece becomes x plus h squared because our function is the square function and we're just plugging in x plus h and squaring it. I'm subtracting from this f of x, which is just x squared. And I'm dividing by h. Okay, now in order to calculate this limit, I need to simplify this quotient here. And if I square this binomial, I'm going to have to use the FOIL. So let me just do that over here on the side so you can just kind of an algebra review for you. X plus h squared is x plus h times x plus h. And so the FOIL method, the first terms are 2x's multiplied gives me x squared. Then the outside is x times h. The inside is x times h. So that's going to be combined to be 2xh. And the last is h times h, or h squared. So this is going to go right here. And then I'm going to subtract off my x squared. So you'll notice the x squared minus x squared, that cancels. Those are 0. And we are left with 2xh plus h squared. But notice I'm dividing by h. And this has a common factor here of h. So what I want to do is factor out the h from the numerator. And that leaves me with 2x here plus 1h here. And as you can see now, my h's will cancel. And this becomes the limit as h approaches 0 of 2x plus h. So what have I done right here? I've calculated the derivative for any x, okay? So if h is going to 0, then I just plug a 0 in. And so the derivative is the function. So the derivative, f prime of x, is another function, which is 2x. So our original function is x squared, and the derivative is also a function. This time it's 2x. So if I want to find the slope of the tangent line for our function at x equal 1, then I need to plug in the 1 for x. And I get 2 times 1, right? I'm taking x and putting in a 1 in place of the x. Okay, this is the slope of the tangent line at x equal 1. Okay, and I can just draw you a picture to show you what that looks like. Just a little picture right here. So we have our function, and at x equal 1, let me draw it in a different color. We have the tangent line. So what we found is the slope of this red tangent line here, the slope is 2. We're not quite done yet. We still have to find the entire equation, but we're working towards that. We found now that the equation of this line, remember the slope-intercept form of a line is y equals mx plus b. We just need to find m and b. Well, we found the m. The m is 2. So we have y equals, I'm going to write the 2 in there for the slope. Okay, now we just need to find the b. Okay, well, how do we do that? Well, we know that this line has slope 2 and it passes through this point here. This point is 1, 1. When x equals 1 and you square it, y equals 1 also, because 1 squared is 1. So this point is 1, 1, and I can plug the x and y values into my equation, and that will allow me to solve for b. Okay, so I'm going to plug in 1 for y and 1 for x. And that gives me 1 equals 2 plus b. If I subtract 2 from both sides, I get that b is equal to 1 minus 2, or minus 1. And that agrees with our graph. Notice that the red line intercepts the y-axis right here at -1. Okay, so we found the equation of our line, our tangent line, the red one. Y equals 2x minus 1. This is something that you're going to do a lot throughout this course, is finding the tangent line. So these steps are, now we will not be doing, after today, we will not be using this method right here to calculate the derivative. We are going to come up with some rules that are much easier for calculating the derivative. But this is the definition. So here I'm calculating it by hand directly from the definition. But if you apply the definition to different types of functions, you'll see there are rules that you can follow, and it saves you a lot of steps of messy algebra and things like that. So that is how you find the tangent line for a function given a point. Now I wrote step 1 here. Step 2, I suppose, would be to find the b. Step 1 is find m, and step 2 is find b. Okay, any questions on this before we move on? All right, let me do another example. This time I want to find the tangent line to the curve of the function negative 2x cubed. Okay, so again, we're given a function, we're given the point, and we want to find the tangent line for the function at that point. So step 1, since we're looking for a line, is to find the slope. Okay, this would be the derivative. And remember, the definition is the limit as h approaches 0 of our difference quotient and for our particular function, we have negative 2x cubed so we're going to take negative 2, and instead of x cubed, I'm going to put x plus h in for my x. And then here I'm just subtracting f of x, which is negative 2x cubed over h. Okay, so I need to simplify this fraction. And the first thing I need to do is to calculate x plus h times x plus h times x plus h. That's the x cubed right here. Okay, this by the FOIL method we did on the other page, remember, this is x plus h squared. We got x squared plus 2xh plus h squared multiplied by x plus h, okay? And so now we're going to have to multiply those two. This is a trinomial times a binomial. So here we have a 3-term polynomial, here we have a 2-term. 3 times 2 is 6, so we're going to have 6 new terms. So first we're going to take x times each of these terms, and then after that we're going to calculate h times each term. So that's how we get our 6 terms. So x times x squared is x cubed. X times 2xh is 2x squared h. X times h squared is xh squared. Then we have h times x squared. So I'm just going to write it as x squared h. H times 2xh is 2xh squared. And finally, h times h squared is h cubed. Okay? Now I'm going to combine like terms, and I get x cubed plus 3x squared h plus 3xh squared plus h cubed. So this is x plus h cubed. Oops, I forgot my h there. Now notice I have a double negative, so this is going to be plus 2x cubed. And I have to be careful here. This negative 2 is multiplied by this, so I have to make sure I put my parentheses in there because I don't want to multiply this by negative 2. Okay, the negative 2 is just multiplying here, so I've got my parentheses in. Now I want to go ahead and distribute the negative 2 like that. And I get negative 2x cubed minus 6, because I have negative 2 times 3, x squared h plus 6x h squared. Oops. Notice I have negative 2 times 3, so that should be a minus. That's a minus there. Plus h cubed plus 2. There are a lot of opportunities here to make mistakes. But the nice thing about this, when you are simplifying your difference quotient, you know you can catch those mistakes because anything that doesn't have an h in it is always going to cancel in the numerator. And you can see that happens right here. We have negative 2x cubed. There's no h in there. And here we have 2x cubed. There's no h, but those combine to be 0. So I can cancel those, okay? Everything else has an h in it. Now I can factor this h and cancel. So I'm going to do that next. And let's see, I get, taking an h out here leaves me with negative 6x squared. And then taking an h out here, negative 6xh. And taking one out here is h squared. So now my h's cancel. And this becomes the limit as h approaches 0 of negative 6x squared minus 6xh plus h squared. Now to find the limit, I use substitution. This is a polynomial, it's continuous, so I know that the limit is going to equal the function value. So I just plug in the 0. There's my h, 0, 0. This is all going to be 0 after I plug in h equal to 0. So all that I'm left with then after I take the limit is negative 6x squared, okay? Now this is the derivative for the function for any x. We want to know what is the slope of the tangent line at x equal negative 1, because here's our point, negative 1, 2. So x is negative 1. So we want to go f prime at negative 1, and we just plug in negative 1, square it, and that becomes negative 6. Okay, so this is the slope of the tangent line. At x equal negative 1. In other words, the point negative 1, 2. Okay. So now we just have to, step 2 is find b. So we have a y equals mx plus b. We plug in the slope, which is negative 6. So y equals, I'm just going to write that in red to highlight the fact that I found it here in this step. Y equals negative 6x plus b. So now I just take this point and plug it in for x and y, and that gives me 2 equals negative 6 times negative 1 plus b. So I have 2 equals 6 plus b. Sorry about that. So we're going to subtract 6 from both sides, and we get b is equal to negative 4. Probably should have used a different color. This negative 6 is not the same as the slope. I'm just subtracting. Okay. So the slope, or the equation for our tangent line, at negative 1, 2 for f of x equal negative 2x cubed is y equals negative 6x minus 4. So let's just take a look at the graph of that. I'm going to share my screen and we're going to go to Desmos and take a look at that. Let's see here. So my function is y equals negative 2x cubed. Okay, there's my function. And then I'm interested at the point, finding the tangent at the point. What was it? Negative 1, 2. Okay, there's my point. And so the tangent line is going to be passing through the point and touching the graph, not crossing the graph. Okay, so it's going to be y equals negative 6x minus 4. And there you can see it. All right. So any questions? Feel free to unmute yourself if you want to chime in there. Like I said, this is a long process of going through this, but starting today, this is the last time you're going to have to do this. So here I'm showing you how to calculate the derivative directly from the definition. But starting today, we're going to be developing some rules where you won't have to do that because this is kind of a lengthy process, okay? Now, I'd like to show you how to find the derivative for a linear function. All right, so notice that I'm not talking about a particular linear function. I want to find the derivative for any linear function. So if I can do it for any linear function, then, that's an easy way of finding the derivative. So what is a linear function? Well, a linear function has the form f of x equals mx plus b, okay? And I don't really care what m is or b. I want to find the derivative for any linear function. So I'm going to take my definition and apply it to this type of function. And remember, the definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And to evaluate the function at x plus h, I just take my x plus h and replace the x here. So this is going to be the limit as h approaches 0 of m times x plus h. Right here we have mx, so I'm just replacing the x with x plus h. And then, of course, plus b. And then I'm going to subtract my function, which is mx plus b, divide that by h, and this is a b, by the way. And that's going to become the limit as h approaches 0. So now I need to distribute the m through, and then distribute this negative through. So I'm going to get mx plus mh plus b minus mx minus b all over h. And remember I said if it doesn't have an h in it at this point, anything without an h needs to cancel. And it does, because look here, we have mx minus mx. And then we have b minus b. So we are left with mh, which has an h in it. And that's what we want, because now we're looking for the limit as h approaches 0 of mh divided by h, which is just plain old the limit as h approaches 0 of m. But if for a constant function, the limit is the constant, right? So it turns out that the derivative for any linear function is its slope. That's the implication. The derivative for any linear function, that's the key word, linear function, is its slope. All right. And that makes sense, right? Because if you have a line and you try to draw a tangent line next to the line, then obviously it's going to be the same line. So you have a linear function. Just some line. If you try to pick a point and draw a tangent, it's just going to be that same line. Okay. It touches the graph but doesn't cross it. It just, well, it lies on top of it. It's the same line.